If you'd like to have access to my entire ArduPilot tuning course in PDF format, and that's not just the content in this video, but the entire course, then that PDF is available on my Patreon, and I'll put a link to that down in the video description. It really is the perfect accompaniment to this video series, and it's nice to have it on the bench next to you while you're tuning, so you can quickly refer to it to see what the terms are called that you need to adjust and where to find them. If you're looking to tune larger drones for professional applications, then you might also want to consider my ArduPilot tuning course, and I'll put a link to that down in the video description as well. That's going to cover tuning larger drones in more detail and using some of the more sophisticated tools in ArduPilot to achieve that. Hi there everyone, and welcome back to the channel. This video is the third part in my complete ArduPilot tuning guide. In the first two parts of this video series, we've looked at setting up ArduPilot for the first time and tuning the gyro filters for the best possible flight performance. But now it's time to move on to PID tuning. In this video, we're going to be going through all the different PID controllers that are in ArduPilot. We're going to be looking at how they're set up and the different components that we're going to need to tune. We're going to be going into a little bit of PID tuning theory so that you understand what all the different terms do and how you should adjust them depending on what you see in the logs. And then we're going to be going through a methodical tuning approach, starting with the rate PID controllers and working our way up. It's a lot to cover in this video, so let's not waste any more time. Let's dive right into it. Before we dive into the theory of PID tuning ArduPilot, I just want to give you some background on all of the different PID controllers that ArduPilot has inside it. ArduPilot uses a cascade of PID controllers to control the position, the velocity, the acceleration, the angle, and the rate of rotation of the drone. And to get good autonomous flight performance, you need every single one of these PID controllers to be correctly tuned. And so we're going to start at the bottom and work our way up. And that's the way that we have to tune these things, because you can't tune these higher level controllers if the lower level controllers are not performing brilliantly. Before we dive into manual PID tuning, I would be remiss if I didn't mention the ArduPilot Autotune functions. Now, ArduPilot has a couple of different auto-tuning scripts which try to find reasonable PID values for the rate and angle controllers. In general, these tools can produce suitable tunes for hobby use on small drones, but they often struggle with larger drones, drones that are slower to respond, and they can produce suboptimal tunes which in rare cases can be dangerously unflyable. A methodical manual tuning approach is always going to give you a better result than what you can achieve with Autotune. You as a human have much more information available to you in the log file that helps guide the tune, and you can also access more parameters, adjust more parameters that Autotune doesn't touch, which allows you to get a tune that gives you much better flight performance. Manual tuning and that methodical manual tuning approach is what we're going to cover in this guide. Before we dive into the methodical tuning approach for the rate PID controller, which is the first one we're going to look at, it's important to have a theoretical understanding of PID control, an understanding of what all the different terms are within the PID controller and what they do, so that we know how to adjust them to achieve the desired outcome, the desired effect. This diagram shows you a schematic of the rate PID controller in ArduPilot. On the left, we have the two inputs. The first is the target rate of rotation. This is how fast the quad is being asked to rotate around each axis. And that target rate of rotation can come from the pilot stick inputs in acro mode, or more likely from the angle controller when you're flying in any of the other modes. The second input is the actual rate of rotation, and that comes from the gyro in the IMU on your flight controller. This tells the quad how fast it's actually rotating around each of the axes. So we have the target and the actual rate of rotation. These are fed into a number of different terms. We have the feedforward term, the derivative feedforward term, which looks at the time derivative of the target rate of rotation. And then we also have a PID error term, which is calculated by subtracting the actual rate from the target rate to get an error. And that is then fed into two terms, a proportional term and an integral term. The integral term looks at the time integral of PID error. And then we also have a derivative term, which is just the time derivative of the actual rate of rotation. All of these terms are multiplied by different gains, which we're going to set in the ArduPilot software, and then they are all added together to give a commanded control output, which is going to be fed into the motor mixer, which will drive the motors, and that will command the quad to do the correct rotation. If all of these terms are correctly balanced, then the quad will follow the target rate of rotation very, very closely. If any of these terms are incorrect, they've got the value that's too high or too low, then the actual rotor rotation won't follow the target rate of rotation very well, and the drone won't fly well. So the whole purpose of the methodical PID tune is to get the actual rate of rotation to match the target rate of rotation as closely as possible by tuning the gains of all of these different terms. Now that we've seen each of these terms in the schematic, let's dive into how each of them behave, starting with the proportional term. The proportional term acts on PID error, so the PID error is the difference between the target and actual rate of rotation, and it simply is a multiple of the PID error. So the larger the PID error gets, the harder the proportional term pushes back towards the target. So if the PID error is positive, then the proportional term will push to reduce that error and try and bring it down to zero. The P term acts like the spring in a suspension strut. The further away the actual rate of rotation is from the target rate of rotation, the bigger the P term gets, and it's always pushing to try and reduce that PID error. The next term we're going to talk about is the derivative term. And the derivative term wants the actual value of the rate of rotation to stay the same all the time. So the derivative term, the D term, pushes back against any change in the actual rate of rotation. So if the actual rate of rotation is increasing, the D term pushes to try and slow the rate of that increase. If the actual rate of rotation changes a lot, then the D term becomes very large and it pushes back against that change. The derivative term acts like the shock absorber in a suspension strut. It's always looking to slow down how quickly the quad responds or the drone responds to any input, and to keep that actual rate of rotation as low as possible. Just like in the suspension strut for a car or bike, the balance between the spring, the P term, and the shock absorber, the D term, is very, very important. If you have too much P term, then everything's going to be too bouncy and too liable to oscillate. If you have too much D term, everything is going to be very slow to respond. With the correct balance of P term to D term, you get what's called a critically damped response that gives you a very smooth response to changes in input, just like a really nicely balanced suspension strut. The ArduPilot default PD balance is usually a suitable starting point, but can often be a bit heavy on the P term and so prone to oscillate. You're going to have to see how it stacks up for your particular drone, and we're going to be looking at how you tune that PD balance later in this guide. The right balance between the P and D terms is the first step of a really good PID tune for a PID controller. So getting that right is going to be the first thing that you're going to want to look at. Similar to the proportional term, the integral term looks at the PID error. But unlike the proportional term, the integral term adds up the PID error over time and pushes back harder and harder the longer the error persists. We can see in this diagram that we have a small constant positive PID error, and the integral term is pushing back harder and harder and harder as that PID error builds up over time. When the PID error goes negative, the integral term doesn't stop pushing right away, but instead it starts accumulating in the opposite direction, which means that the integral term starts reducing down again. Obviously, if this negative PID error was to continue for a long period of time, we would expect to see the integral term build up in the opposite direction, and again pushing back to try and reduce that PID error to zero. The feedforward term in ArduPilot is another proportional term, but rather than looking at the PID error, the feedforward term looks at the target. The larger the value of the target, the harder the feedforward term pushes in the same direction as the target. This feedforward term helps to overcome resistance that increases in proportion to the target value. There aren't that many situations where that's an important and useful capability to have, but one of them is in the vertical velocity controller. If you're trying to move upwards with a high vertical velocity, then gravity provides a resistance that increases in proportion to the vertical velocity that you're looking to achieve. So in this case, the feedforward term helps overcome that resistance, and it reduces the amount of work that the P term has to do. So you're not always going to need feedforward, but there are certain PID controllers where it can be very, very useful. The derivative feedforward term in the ArduPilot PID controller looks at the rate at which the target is changing. and it pushes in the direction that the target is changing in proportion to how fast the target is changing. The main purpose of the derivative feedforward term is to allow the PID controller to react more quickly before PID error builds up, and if you have derivative feedforward correctly set, it can reduce or even eliminate the delay between changes in target and actual values, and that really helps the controller respond much more quickly to sudden changes in the target. Now that you've seen the theory behind all of the terms in the ArduPilot PID controller, it's time to give you an overview of the PID tuning methodology. We are going to be taking the tune in a certain order. We're going to start with the derivative term, move on to the proportional term, then do the integral term, before finishing off with the derivative feedforward term and finally the feedforward term. The reason we're doing the tune in this order is that there are particular relationships between these terms that need to be respected. The D term prevents the P term oscillating, so there is a correct ratio between the P and D terms. Similarly, the P term prevents the I term oscillating, so there is a correct relationship between the P and I terms. The derivative feedforward term depends on the value of particularly the P term, and the correct feedforward value is going to depend on how tightly the rest of the controller is tuned. By tuning in the order D, P, I, DFF, FF, we won't need to go back and adjust earlier terms based on what we do later in the tuning process. So we have a one-way flow through the tuning methodology. We start with the D term and move through sequentially all the way through to the feedforward term. And once we've done that, the tune is finished. If you do the tune in any other order apart from this, then you may find that you change the P term and then you have to go back and adjust the D term later on, and you can get in a real muddle because there isn't a clear flow and things are dependent on each other. So that's why we're going to be taking this approach going through the tuning process. In order to get the best possible PID tune, it's important to know how to do PID tuning flights. Now, PID tuning flights consist of sharp wobbles on all three axes, and you're going to do the sharp moves by rapidly moving the stick back and forth and then bringing it quickly back to center. When you do these sharp moves, make sure you keep hold of the stick as it comes back to center. If you just release the sticks and let them kind of bounce back to center under their own spring action, they can oscillate and bounce around the center, and that can make the drone oscillate, which might make you think you have too much P gain when you actually don't. You can do these sharp moves in stabilize mode. I would suggest that that's the best, or you could do it in altitude hold. But if you're doing it in altitude hold mode, that does rely on the altitude controller being reasonably well tuned to begin with, which it may not be. If you're getting any oscillations, try switching to stabilize mode, because that will take the altitude controller out of the equation and will allow you just to be looking at the rate and angle PID controllers.
So for a typical PID tuning flight, you're just going to want to take off and hover in stabilize mode, and then give the drone small oscillations, first on the roll axis, then on the pitch axis, and then finally on the yaw axis. And just do that for maybe 10 to 20 seconds on each axis, and then bring the drone into land. That's all you need to do for a PID tuning flight.
Once you've finished your test flight, it's time to land and then download the log using MissionPlanner the way we did before, and open the log file in ArduPilot Web Tools PID Review. So you can do that by just going and clicking the Choose File button, selecting the log file that you downloaded with MissionPlanner, and then loading it in. Check that the flight data graph, which should appear immediately after you've loaded in the log, looks correct, that it kind of reflects what you did during the flight, that there are no gaps or logging dropouts, and that everything is working correctly. Once you've done that, select the PID roll, PID pitch, or PID yaw graph to look at, and I would move through them in order. So start with roll, then move to pitch, and finally yaw. When you scroll down to the time domain, you'll see a graph that looks something like this. And you can see that it's pretty much completely unreadable at the default zoom level. You're going to want to zoom in on a part of the flight where you were wobbling the drone on the target axis, the axis that you're looking at right now. So let's say we're starting with the roll axis. You're going to zoom into a part of the flight where you were doing those sharp wobbles on the roll axis. Once you've zoomed in to the right amount, you should see a chart that looks something like this. You should be able to see the target in blue, the actual in orange, and the error in green. The goal is to get the actual to sit directly on top of the target, and that's what we're going to be trying to do as we go through our PID tuning process. It is possible to tune PD balance, and in fact to tune all the PIDs using only time series data. And it's actually useful to learn how to do this because for some controllers, like the throttle controller, we will only ever have access to time series data. We're not going to be able to get step responses or anything like that because the tooling doesn't really exist for it. So if you can learn to tune using just time series data, that's great, although we will also be using the step response as well. When we're tuning PD balance based on time series data, what we're going to be looking at is the relationship between the actual value and the target value. We will find that without any derivative feed forward, the actual value is always going to lag behind the target value a little bit. And that's okay, that's normal, that's what we want. What we need to look at is the relationship between the actual peak value and the target peak value in the time series data to determine if we've got the right PD balance. If you look at the waveform for the target and the waveform for the actual, and you see that the peak of the actual graph is bigger than the target graph, that indicates that you have too much p-term. So your PD balance is too p-term heavy. So you need to reduce your p-term or increase your d-term. If you have a target graph that is larger, the peak is higher than in the actual graph, like this one down here, then that means that your PD balance is too d-term heavy. Your d-term is too large, and so that's meaning that your actual movement of the quad doesn't ever reach the same peak level as the target is requesting. If you have the ideal PD balance, what you'll see is that the target peak and the actual peak will be of exactly the same amplitude. If you're seeing this, so the actual is delayed a little bit from the target, but the peak value is the same, then that means that your PD balance is exactly correct, and that means that you can move on to the next stage of tuning that axis. It's also possible to tune the PD balance using the step response, and if you scroll down in ArduPilot PID Review, you'll find the step response graph. You'll see lots of faint grey lines and then one blue line, which is the average of all the grey lines. What we're looking for is to have the blue line rise as quickly as possible to the 1.0 level and then just continue straight flat from there. If we look at this chart down here, you can see that if we have a graph like this green line where we shoot way past 100% or 1.0 and then bounce up and down for a long time, that indicates that we have too much p-term. If we look at a line like this purplish line here that kind of takes a long time to gradually reach up to 1.0, that indicates that we've got too much d-term. And so we need to either increase p-term or reduce d-term. If you have something that looks like the red line, which is a rapid rise to 1.0 without any overshoot, then that indicates that your PD balance is correct and you have the right ratio of p-term to d-term. So you can use a step response. This is giving you exactly the same information as the time series data that we were looking at previously, just in a different form. Some people find it easier, but for different controllers on ArduPilot, you will eventually have to do some PID tuning using only the time series data, so it's good to practice that if you can. It's important to know when tuning the PD balance that it is the ratio between the p-term and d-term that is important, not the individual values. I would suggest only changing the p-term while you're tuning the PD balance because that will keep things very simple, and if you change the p-term, of course you're changing the ratio between the p and the d-terms. You can do this in MissionPlanner config extended tuning, and you can just kind of move the p-term up and down. Unless you have a completely symmetric drone, the pitch and roll values are likely to be a bit different. So you can probably unlock the pitch and roll values and then tune them individually. Especially the more asymmetric your drone is on pitch and roll, the more different the ideal PD balance for pitch and roll is likely to be. If during this process you find you are suffering from oscillations, so the quad is kind of oscillating on one of the axes, and you reduce the p-term and the oscillations don't improve, then this could be two things. You might be experiencing d-term oscillation. If your D gains are too high, then the d-term can self-oscillate independent of the p-term, and in that case reducing the P term doesn't help. To fix this, reduce both the D and P terms in steps of 10%. So divide the D and P term by 1.1 and see if the oscillations improve. And if they do, keep dividing the D term and P term together by 1.1, because you're keeping that ratio the same, but you're reducing the values until the oscillations go away. Excessive filter delay can also cause oscillations. Now, hopefully if you followed through my gyro filter tuning video, you should not have excessive filter delay. But if you haven't looked at the gyro filters yet, you may want to go back and watch that video and make sure that you've got your gyro filtering as clean as it possibly can be, and you've got the delay of the gyro filters as low as you can possibly get to avoid oscillations due to excessive filter delay. But that's another thing to check. Once you've found the overall correct PD balance for the pitch and roll axes, we're going to want to try and increase the overall PID gains to improve the responsiveness of the quad and reduce PID error. We want to do this without changing the ratio between the P and D terms that we've already found. And so the way that I would suggest you do this is to increase P, I, and D by the same multiple. So to find the new P term, multiply the old P term by 1.1. That's an increase of 10%. For the I term, again, it's the old I term times 1.1, and the new D term will be the old D term times 1.1. Because we're multiplying all of the values by the same multiple, the ratio between P term and D term and the ratio between P term and I term won't change. And that means that the step response of the quad also shouldn't change. We're just increasing those PID gains, tightening up the PID controller and reducing PID error whilst keeping that critical PD ratio exactly the same. Keep increasing P, I, and D using this rule by just multiplying by 10%. Until you start to see oscillations coming in the logs, and the quad will kind of feel very, very tight, and you will start to hear little sort of trilling oscillations, particularly after sharp moves. Once you start to hear or start to see oscillations in the logs, back the PI and D gains down by 10 or 20%. What you're looking to find is the maximum value for the PI and D gains where you don't see any hint of oscillation at all, and that's the ideal value. You're going to need to adjust the roll and pitch axes separately, because unless your quad is perfectly symmetric, you will have a different maximum PI and D gain for the pitch and roll axes. In many cases, increasing the overall PID gains with the correct PD balance is going to give you a pretty drastic improvement in flight performance. And hopefully this should tell you that you're on the right track with your tuning. Now that you've found the overall maximum PI and D gains for your quad, it's time to look at the I term. Now the I term typically has a very wide tuning window, so it is not always necessary to directly tune the I term once you've found the absolute PID gains, the magnitude of them that works really well. However, theoretically increasing the I term can give target tracking improvements, because it means that that I term responds more quickly to help reduce consistent errors between the target and the actual value. I term should be increased gradually in steps of 10 to 20% until you see evidence of I term oscillation in your logs, and then you need to back it down again. Each axis is going to need to be adjusted separately, and again, unless you have a perfectly symmetric quad, you may find there's a different maximum I term for the roll and pitch axes. Tuning the yaw axis is a little different from tuning pitch and roll, because the yaw axis typically has significant physical damping in the system. It's a lot less responsive than pitch and roll as a result. And this means that we don't typically need a derivative term on the yaw axis for multicopters. We're only going to be working with proportional and integral terms, P and I terms. This means that we only need to consider the PI balance and overall gains when we're tuning the yaw axis. And the way to do this is, again, to increase the P and I gains together, stepping up in steps of 10%, keeping the ratio the same, until you see oscillations, and then backing the gains down 10, 20%, until you don't see oscillations anymore, but the gains are as high as they can be. And then once you've done that with both the P and I gain together, you can then, if you want to, attempt to increase the I term individually up a little bit more, again looking for any oscillations in the logs. You may find that you also want to reduce the yaw error filtering on the axes in order to improve the responsiveness of the yaw axis. Now, tuning the PID filters, so the error, derivative, and target filters, is a more in-depth topic. I'm going to cover that in more detail in the ArduPilot tuning course that I'm going to link down in the video description. But in general, for small quads, you won't need to adjust those PID filters. At this stage, you should have a really excellent rate PID tune on your ArduPilot drone. And that tune is going to set you up with a really great foundation for tuning all of the higher level PID controllers. Hopefully you are already seeing a big improvement in flight performance, not just in acro mode, but also in stabilize, loiter, those higher level modes, because they really do benefit from a really tight rate PID tune. Now we're going to look at the attitude controller so that we can get the drone completely tuned in the stabilize mode. Increasing the absolute value of the PI and D gains will help make the quad more responsive, and for smaller quads, that's probably going to be all you need. For much larger quads, they are less responsive and they can really benefit from something called derivative feed forward, which is another term in the PID controller that helps reduce delay. Now, I'm not going to cover tuning derivative feed forward in this guide because, as I said, it's not really suitable for smaller hobby grade drones, and it's a more sophisticated tuning topic that needs its own video, because we also need to cover tuning the PID filters in ArduPilot as well at the same time, and that's another big topic. Again, it's not really necessary for hobby drones with prop sizes up to 8 inches. If you're interested in learning more about tuning derivative feed forward in ArduPilot and tuning the PID filters, then check out the links down in the video description to learn more about my ArduPilot tuning course, where I am going to be going into that in much more detail. Now let's talk about tuning the attitude controllers. And the attitude controllers are simple proportional controllers that control the angle of the drone relative to the ground for the pitch and roll axes and relative to north for the yaw axis. The difference between desired and actual angle is multiplied by a factor to give a target rate of rotation, and that target rate of rotation is passed through into the rate PID controller. So to show that in a schematic, we have the desired angle and the actual angle. Those are subtracted to give an angle error. That's multiplied by the proportional term, and that's the target rate of rotation that is passed into the ArduPilot rate controller for pitch, roll, and yaw respectively. You can tune the P terms for these controllers in the config tab in MissionPlanner under extended tuning. And you can see here stabilize roll, stabilize pitch, and stabilize yaw. You'll have a P term. If you increase the P term, a larger value will give a more aggressive response to angle errors. But if you make the value too large, it will cause oscillation on the angle axis. So again, you're just going to want to increase these P terms just as high as you can until you start seeing a hint of oscillation, and then back down 10 or 20% or so to ensure that you have a stable response of the quad. It's really useful to be able to look at logs while you're tuning the attitude controller P gains, and you can review the desired versus actual angles. They are logged in the attitude section, ATT, and if you go into review a log in MissionPlanner, it'll bring up this window. If you search for the ATT section on the right hand side, and then you can find the desired roll, desired pitch, desired yaw, and the actual roll, actual pitch, actual yaw. And that will allow you to look for any oscillations or overshoots that you might be able to see in the logs that might indicate that your attitude P gain is too high. Again, you're going to want to tune each axis separately unless you have a perfectly symmetric quad, in which case the pitch and roll axes are likely to be the same. You'll also see in the extended tuning tab that underneath the P terms, you have Excel maxes for roll, pitch, and yaw in the stabilized mode. And ArduPilot provides these limits for the maximum rate of angular acceleration demanded by the attitude controller. So if you have a very large difference between the desired angle and the actual angle, such that the P gain would produce a value larger than this Excel max value, then ArduPilot limits it to Excel max. These Excel max values should be set according to the capability of the drone, and calculating these values for larger drones is critical, and it's covered in detail in my ArduPilot tuning course. So if you're looking to tune a large drone, then it's worth making sure that you cover that. Small drones like hobby drones up to like an 8-inch prop size can safely disable these limits because small drones can respond quickly enough that you're never going to see the P gain produce a desired acceleration that is larger than the drone can deliver in normal flight. To disable these values for small hobby drones only, you can set this value to 0. So you just set Excel max to 0, that disables the limit. Don't do that for larger drones. For larger drones, make sure you look through the ArduPilot tuning course and calculate the correct maximum value. The final thing to look at with the stabilized controller is the maximum lean angle. This is the maximum angle that ArduPilot will allow the drone to tilt over in stabilized mode, and the maximum lean angle should usually be set to ensure that the drone has plenty of thrust to maintain altitude and control even when it's at the maximum lean angle. A good way to calculate this is to take the maximum lean angle as inverse cos of the weight of the drone divided by 80% of the maximum thrust. This means that the drone can maintain altitude at the maximum lean angle using only 80% of the maximum motor thrust, and that gives you 20% left over for control. You may find for drones with a high power to weight ratio, high thrust to weight ratio, that this equation may give very large angles of 45 degrees or even more. For most applications, I would recommend a maximum angle of 30 degrees is more than sufficient, and larger values like 45 or more can be concerning for pilots because it is a bit shocking to see the drone lean really right over in the sky, even if it is actually capable of maintaining altitude under those conditions. Once you've calculated or decided upon the maximum lean angle, you just need to set it up in ArduPilot. And to do that, you're going to go into the full parameter list in the config tab in MissionPlanner and look for the angle_max setting. This angle_max is the maximum angle allowed in all modes, and it's in centigrades. So 30 degrees is 3000 centigrades. You're also going to want to set PSC_angle_max. That's the max angle allowed in position hold mode. I would set that to 0, and that's going to use the same value as you set in angle_max. For loit_angle_max, that's the maximum pilot requested angle that's allowed in the loiter mode. Now, if you set it to 0, that's going to use 2/3 of angle_max, and that will mean that the drone will feel more sluggish in loiter mode compared to stabilize. And I don't recommend that. I don't think that's a good flight experience for the pilot. So I would generally recommend setting angle_max to 3000 centigrades, that's 30 degrees, PSC angle max to 0, so the same as angle max, and loit angle max to 3000 centigrades, the same as angle max, and that will give a consistent flight feel in all the modes. At this stage, you should have a really excellent acro or rate PID tune on your drone, and the drone should be well tuned in stabilized mode as well. In the next part of this video series, we're going to be looking at the throttle PID controller so that we can get a really responsive and precise tune in altitude hold mode, and that the drone can change altitude really quickly and accurately. Until that next part of the video, please check out the links down in the video description to see the full ArduPilot tuning guide in PDF format. So not just the content in this video, but all of the content in previous and future videos is currently available in PDF format. And also check out the links to learn more about the ArduPilot tuning course, which covers some of the more sophisticated topics that we haven't looked at in this video that are more appropriate for larger drones, like feedforward tuning, PID filter tuning, and calculating maximum angular accelerations. That's all I have for you in this video, so until next time, I wish you all very, very happy flying.